Hello everyone. Today I am presenting a paper published on how to use a machine learning model on Google Cloud to estimate rainfall. So basically our primary objective of this study is to harness the power of cloud computing and machine learning methodologies to fill the crucial gap in rainfall data in areas where traditional meteorology stations are not available, with a specific focus on the region of Assam. So the Assam, a vibrant state in northeastern India, as you can see on the map, world map. The coordinates are 26.2006 degrees north latitude and longitude is 92.9376 degree east. The climatic details here are Assam experience a humid subtropical climate and annual rainfall ranges from 2000 to 3000 millimeters. Here are the features used for the machine learning model to predict the rainfall. The primary target or dependent variable for the study is a graded rainfall data sources from the Indian Meteorology Department IMT. The features used here are LST, LS, WI, MNT, WIND, VIND, WI, TCI, VCI, and WRI. The LST is land surface temperature, that is radioactive skin temperature of the land derived from infrared radiation. The second one, LSWI, is land surface water index. Use the surface infrared and the NIR region of the electromagnetic spectrum. And the second one is MNDWI. This one effectively differentiate between water and urban areas through the satellite imagery. Next one is NDVI, that is normalized difference vegetation index. This metric quantifies the health and density of the vegetation in that area. Next one is NDWI, that is normalized difference water index, is an index for monitoring content changes in surface water. The next one is TCI, that is temperature condition index, used to determine stress on vegetation caused by temperature and excessive wetness. Next one is VCI, that is vegetation condition index, compares the current NDVI to the range of the values obtained in the same period in the previous year. WRI, the last one, which is water ratio index. This index can be used to determine the amount of moisture in the vegetation. So next step is to create a machine learning model, for which we have already selected features as discussed in previous slide. And now after data extraction and preparation, there comes a part of prediction. For predicting, we have used derived from the data Landsat 8 imagery using Google Earth Engine GEE, that is a GCP service, and we have extracted terrain STDMDEM from NASA, and after that we have split the data into 70-30 ratio, that is 70% of the data was kept for calibration and 30% of the data was kept for validation. Calibration means a data on which we train the model, and validation means data on which we test the model. The fourth step is to fine-tune the SVR algorithm, that is support vector regression. Here they have applied SVR using E1071 package in R environment as stated in the paper. After that, they have used feature selection using RFE, that is recursive feature elimination. Then they have selected a kernel function to transform data into higher dimension space for non-linear relationship. The final part of the model building is the model performance evaluation, for which they have used a 10-fold cross validation, which is like if we split the data into 10 and we use the first part as a test and rest of the data for train, and doing this same for 10 folds means repeating the same step 10 times using different set as a test set. A little about the support vector regression. From definition, SVR is a regression algorithm derived from SVM, that is support vector machine, predicting continuous values. Key concept here is the hyperplane kernel trick and epsilon insensitive losses. Determine input output relation and capture complex pattern and tolerant outliers. Workflow, as we discussed in the previous slide, is same: data pre-processing, kernel selection, model training, and prediction. Advantage of using this support vector regression was the model is very robust to outliers, as it only consider to create a decision boundary the nearer data points and handling high dimensional data. Now here comes the use of Google Cloud Service, that is GEE, Google Earth Engine. Here they have used the Google Earth Engine for deriving spectral indices for Landsat 8 imagery. Here's how GEE is involved. There are three main features or main tasks performed by the Google Cloud Service, that is GEE. The first one is access to satellite imagery. GEE provides access to vast archive of satellite imagery, including Landsat 8 data, which is crucial for obtaining spectral information. Second is image analysis and processing. GEE allows us to perform complex image analysis and processing task directly in the cloud. In our case, it uses for calculating spatial indices like ND, VI, LS, WI, etc., which we used as a features. Third main feature is scalability and efficiency. GCP's cloud infrastructure ensures that their computationals are performed ineffectively, leveraging the scalability of the cloud resources. So here are the results and discussions. Model performance matrix is as follow. As we can see, validation data R square was given as 0.27 and root mean square error, that is RMSE, is 328.68 mm. Mean square error is MAE 295.10 mm. Implications and limitations are as follows. SVR effectively predicted 2020 Assam rainfall by varying error of 300 mm. That is very small as compared to the actual data, as the output was in range from 200 mm to 300 mm. Implications we can make is crucial for decision making in data scarce area. Limitations of this was like the data set we use. For example, for instance, the rainfall's complexity and stochastic nature. And on the left you can see this is the predicted rainfall from the model we built, that is SVR, support vector regression. In conclusion, the paper successfully employed a cloud computing and machine learning to estimate missing rainfall data in Assam. Key findings are SVM model demonstrates effective in predicting annual rainfall for 2020 with a very low mean square error and root mean square error. Practical significances are crucial insights for farmers and decision makers in data scarce region. Second is localized rainfall predictions contributes to effective resources management. Thank you.